Thank you. So yesterday I did a lot of live demo stuff. Today, all slides, so don't worry. But a little bit of background on this whole talk and why it exists is that I write a lot of APL code. And I primarily write a lot of APL code for a compiler that's written in APL. And it's designed to self-host itself on the GPU. And almost all of it is branchless, loopless, doesn't do any like data type abstractions that you would typically think of. All the typical things you think you need to write a compiler, I'm not using it. And so one of the things that's missing, essentially, is what we would typically think of as syntactic control flow. These kinds of markers, this might be a for loop, or pattern matching with recursion, or any of that stuff, that's all gone. We don't do that. And the reason is partly because I think it's a better way to program, but also we get these sort of benefits, or at least we try to get these benefits from the writing code in this way, because it's a simpler architecture, and the biggest early benefit was that this is naturally a data parallel way to write our code, right? So if you don't have all of this control flow and loops and everything, it's much easier to parallelize. It's much easier to get it onto the GPU. And if you don't have all this data type abstraction, you reduce your memory footprint, which reduces your memory requirements on memory-bound operations, which means you tend to be a lot faster. One of the ways we do that is getting rid of generalized pointers. So we don't use pointers generally in the system as an abstraction concept. And because the code ends up being so small, it's really maintainable and it's very portable. And I claim that APL is basically the best language for this, and that I would even go so far as to say my hypothesis is that APL is the only reason I was able to write code like this. And that if I had tried to do this at scale with another language, it might not have succeeded. It probably would have failed. And the question is why? Because APL as a language is very simple. And we're going to go over enough so you can appreciate APL as a simple language. So then what makes it actually enable somebody to think and write a program like this, and why do I think that it's one of the best languages for doing this? And unlike other languages, I'm not going to focus primarily on semantics. I specifically want you to shift your whole perspective on this right now and think not about the semantics of the language, but about the experience design, the UX of the language, right? From a human-computer interaction design, what does it feel like to use a language like this? And how is the various elements, how do they fit together to support what I'm trying to do, which is essentially I'm trying to do larger scale data parallel, loopless software as a general technique, not as a special technique in particular domains, but as the general way that I'm going to program my software, and only drop into sequential loopy code or if statement code or branching code if I really need to. So that means we want to focus on this unique ergonomic affordances that the language gives you as a result of its design. And that means what are the handles that you get, and what are the things that you do to use the language and use it at scale. So the reason this talk is being given is because I've given a lot of APL talks in the past, and I've seen a lot of people try to use APL or tried to borrow APL and use it in their language. And a lot of times they fail. If they try to get it into their own language, they almost always fail to get something that's as usable as APL. If they try to use APL themselves, they'll often get stuck somewhere, right? And this is sort of a roadmap of why you get stuck, where you can get stuck, and especially why your translation of APL into your favorite language is likely to fail. Which doesn't necessarily mean that's a bad thing. It's just you should recognize what you're actually getting and trading off. So as a baseline, let's think about what everybody actually gets. What everybody, when they learn APL or they hear about APL and they go look at it, what is the thing that they all actually, we all understand it, they get it, comes back out, they really, this part clicks for them. So if we're going to write a language, right, some kind of computing language, we're probably going to want some mathematical operations, because numbers are a big part of computing. So we start with a language, right? And we're going to want some basic core primitive operations. And right here, you shouldn't be surprised by any of these symbols. This is just math, basic arithmetic operations. And in APL, we say monadic and dyadic, because we like to be Greek instead of Latin, basically. And so monadic doesn't mean monad transformers or something like that. It means unary, and dyadic means binary. And so plus, minus, times, divide, widths would be like remainder or absolute value, floor, ceiling. These symbols are all very straightforward that you would expect, right? But that's not quite enough for any decent programming language. You also probably are going to want some Boolean logic, right? And again, typical Boolean logic operations, nothing surprising here. And we want some comparison operations, so more logic symbols. And just about every programming language is going to have something like this, and a lot of them will have symbols to represent these concepts. But we're trying to write loopless. So if we're going to do this loopless, these symbols naturally have to have some way to become loopless, right? Which means they have to have some way of operating over more than one operation. So we have to introduce some kind of rank polymorphism or cardinality polymorphism over some object that's a collection of some sort of things. And there are lots of ways we could do this. Lisp, for instance, introduced the console. And you could argue that that's how they managed early on to encode more complex compound data. In APL, naturally, we chose the array. And we like the array because it maps directly to very efficient hardware representations. It's a very rich representation, and it's very intuitive to the people who were inventing APL, which were mathematicians doing applied math with a lot of emphasis on linear algebra. And we've been using arrays since like early China and counting with sticks, so it's got a lot of history to it. So I believe that this crowd is capable of handling this, but I do not like to talk about arrays until I formally define what I mean by this. And so I specifically mean an array is a structure that contains two ordered sets. One is the set of elements, which are themselves just members of the set of arrays, and there's at least one of them. And then another is an ordered set of natural numbers, which is the shape that can be empty. And that's arrays as a whole. And that's how I define arrays, and that's what APL arrays are in the floating array model. And we have notation to access the elements. So we put a comma in front of your array, and that gives you the elements of that array. And we put a row, we call it the shape of the array, that gives you back that vector of the natural elements, which are the shape, or natural numbers that are the shape, yes.
So the comma just gives you the elements?
Just gives you a vector of the elements. It's the ordered set as a vector, right? And so we can also access, yes?
Sorry, just to be clear, so the shape is like the rectangular dimensions?
The shape describes a rectilinear space in which the elements are arranged in a row major fashion.
Okay.
Yeah. And so we can also get access to the rank, which is k here, and the count of the array, or the tally of the array as a whole. Tally is incorrect, but really it's the number of elements, which is n, which is just this tally symbol on the ravel. So the tally of the ravel is the number of elements, and the tally of the shape is the rank, which is the number of dimensions in the array. And then we also can access the first dimension with tally itself. So tally itself is just defined as the first dimension of the shape, or 1 if the shape is a scalar or has no elements. And we also have a concept of nesting, right? So you can talk about the depth of how nested an array is, because an array can contain arrays, all the way down to a scalar, which refers into itself. And we can talk about the equality of an array, whether they're equal or not. And so then all we do is we take those last symbols and we lift them up. And the intuition for lifting them up is simply that we apply a map with these scalar arrays over all the elements, pointwise, and preserve the shape. So an example of this is simply that we've got two arrays of the same shape. They're conformable. We multiply them together. We pointwise compute that, and we return something of the same shape. But to make things a little more convenient, we have something called scalar extension, which says, okay, well, if you have just the one item, you can scale that up and just do that over everyone. So everybody gets this about APL. Yes?
Does this work if you, say, had a vector and you could...
Like trying to apply that vector over all the elements?
Yeah.
So see, he's already doing programming language design on this, and we'll get there. right? Because this isn't enough. You immediately think, oh, I want to do more different types of traversals over this. But this rank polymorphic pointwise lifting, we call these the scalar function primitives. Everybody thinks this is APL, right? This is like, oh, that's APL. This is what you do. But if this was all APL could do, we really would be stuck, right? That's kind of a cute trick, but it's only the beginning of how to get more things and make things work, right? So we have to introduce other concepts in any decent programming language to do this. So assigning, looking at the individual elements of arrays or slices of the arrays. Assignment, because we are a effectively functional, very imperative programming language, right? So at least the way I do APL is this way. Now you can make APL do whatever you want. You know, we have all the other stuff too, but I just ignore it and pretend it doesn't exist, and that makes me much more sane. So we need to be able to mutate the array values and elements, and we have the ability to do this by describing the shape that we want to mutate, or we can have a function which describes the selection of the elements that we want to mutate. And we can do this in a sort of functional manner where we can update, or we can produce a new array with certain elements replaced at certain positions. And so that's basically sort of the way you would read something like that is saying, well, take y, find out what elements we want to modify by using the function g, and then use x and the function f combined with those elements to produce new elements that we're going to replace in the same positions in y. And you don't, for this talk, I'm not going to try to teach you APL. So again, don't worry about understanding exactly the semantics of everything that's happening here. Just focus on the overall feel of the types of things that we can do, right? And so again, like this is a perfect example of don't try to fully comprehend this. The basic idea, though, is that if you have these primitives and functions, you probably want to compose them together somehow. So things like being able to commute things, being able to graft things onto each other, compose them into higher order functions, or make connections and function applications of all these. You want to be able to do things like that. So we have ways of combining those together. But, as Ed was mentioning, pointwise isn't the only way that we traverse over elements. And so we would probably want to do more things. So pointwise, we can sort of lift the pointwise concept and reify it explicitly into an operator, which is our each or our map, so that you can use functions, for instance, that are not scalar primitive functions. They don't implicitly have that pointwise lifting. You can do the lifting yourself. Or if you want to apply an element along an axis for particular elements, like if you have a vector that you want to apply along one dimension or another dimension, you can tell it, give it an axis operator. So if we want to sum over a particular axis, you can do something like that. But those are not good enough either, right? Some of the most common patterns you want to do is different types of products, like Cartesian products or inner product. And an inner product is just a rank polymorphic generalized matrix multiply for any definition of plus and times. And I mean any definition of plus and times.
So you don't require any particular mathematical constraints on the plus?
Right. They are well defined even in the presence of non-associative operations, operations with state, operations with mutation, etc. Right? So, but it's a generalized inner product. So the traversal is what you're encoding in the inner product. The traversal and the shape information, or type information. And we also have these types of iterations. So you can run a given function over a given array to change it over time and eventually get to a fixed point. And where G is sort of your stabilization predicate, where the commonest form of a fixed point would be the power equiv, or power match, which is the traditional concept of a fixed point. And we also say, okay, well, we can also slice arrays up in really interesting ways. You can grab subarrays. Maybe we want to do things over each of these subarrays. We can do sliding windows of stencils, right? Or maybe we are kind of databasey, so we want to group by common keys or something like that. And these are all various iteration patterns that we allow to exist in the system, or things like reductions. Or maybe we only want to reduce over a small window of the vectors or of the columns or something like this. Or maybe we actually want to do multiple reduces across prefixes of our dimensions, which is a scan, or like a prefix scan, or what some languages call a cum if you use plus. So plus scan is a prefix sum or a cum. And if you know functional programming, you'll say, oh, well, some of these concepts are in my functional programming language. Sort of. Because the big difference here is we're operating over n-dimensional rectilinear arrays. So we slice and dice, and all of these things operate over lots of different types of array shapes. And they operate in different specific ways, and oftentimes you can't directly encode that concept in the specific reduce primitive or scan primitive that exists in your functional programming language. Instead, you have to map that over the data, and then there's multiple different types of applications to get that access to those patterns. And here, that's all implicit and built into the basic primitives. And we also want to be able to change the structures of this. So these structural manipulations, you can think of these as manipulating the type of the array if you think of the shape as the type of the array. So tabling, catenating, grabbing some elements out and keeping some elements, taking depth, the concept of a depth, and lifting it into the shape, or taking a dimension of the shape and pushing it down into the nesting levels, right? Or flipping and transposing the arrays in various ways, moving them in and out and around and twirling them like some circus freak. That really helps fill out what you might want to do on arrays, right? You want to compute over the elements in various traversal forms, and you want to be able to manipulate the shape to change the way the elements are arranged in various programmatic ways, or change the depth and the types. And that includes things like selecting from various pieces of that. So grabbing things out. Pick is like indexing, except over depth. So pick is a native way to index on the trees of nested arrays. So you can index along shape, or you can index along depth, right? And replicate and expand are different ways of taking elements and repeating them along certain patterns according to a given pattern of some sort, right? And we also have just basic set operations that you would want. And this is a pretty good set of things that you can do with a given piece of data structure, like an array. Like this mostly encompasses everything you would think of as a normal set of operations. But APL takes it one step forward and says, okay, that's also not enough. If we have a basic loopless notation, we want to embed the concept of some of the most commonly used CS theory in our language. So searching is sort of a native concept inside. And actually, the concept of a hash table is also embedded here, right? But basically, this is a way of looking for items in other items, right? And the concepts of looking for intervals or looking for items by identity, and sorting. Now, we have generalized the concept of sorting to grading. So it produces a permutation vector, which you then apply to sort your vector, which turns out to have a lot of interesting benefits to it. And randomness comes in. This is pretty important. Or finding substrings, right? Which we scale out to subarrays inside of our concept, right? And these are all like sort of well-studied areas of basic algorithms for computer science. And we also have one, this is one of my favorites, is the idea of number systems, like base 10, base 2, dates. Anything that has like this radix system, even if it has multiple bases, depending on the position, which is what a date sort of has, we can code those and map them from natural numbers and including negative numbers into these different spaces. And shape is one of these forms, right? So a shape describes a number system to map higher dimensional indices to natural numbers, right? And so this concept turns out to be a really primitive one. It's really useful. And then, basic linear algebra stuff, matrix inverse and matrix divide, we want that natively embedded into our system. So everybody gets that. Well, everybody looks at that stuff, and then they stop, right? So if they're trying to learn APL, everybody can memorize that in about an hour, give or take, if you're good at memorization. Or give yourself a day, and you'll be able to play with that, and it will not feel like it's an insurmountable number of symbols, right? It's like 50 symbols, 100 different functions. It's not actually a lot. But to use those symbols, right? What if I said, all right, now that's all you have. You have function composition, function abstraction. You got to now solve all your problems like that, and you're not allowed to loop anymore. Well, people get stuck on that because they go, like how do you model and get your ideas down? And so we introduced this idea of idioms. And so just like in a natural language where you memorize vocabulary and you learn a grammar, the next step up is you have to learn how to put phrases together that have meaning. And so we put these phrases together and we begin to see pictures in APL of patterns of chains of these primitives, chains of these symbols that give us certain things that we want. So like a little worked example, very simple, is this generating a set of different sets of natural numbers in this combos. And, or this is a predicate that, or a pattern that I use a lot, this where primitive, I can use a predicate, create a Boolean mask over something and get a set of indices about it out. So these are like, the index positions where this thing is true. Just generally speaking. But we have other primitives for doing this. Like we learn, this is the quadratic algorithm for getting the primes up to the number n, right? Or this is how you generate the next generation of the game of life. Or if we have a depth vector representing our tree and we want to get a more rich representation of the parent vectors of that tree, this is our little idiom. Or if we are doing machine learning and we want to do a ReLU 3x3 convolution, we would write something like this, right? But the thing that distinguishes these from what you would see in another language is these are fully defined, and we don't have to always give them names. Often we just insert these inline into the code, and they represent a fairly rich concept. And there are hundreds and hundreds of these that people will learn, and they'll have their pet favorites. But learning these begins to connect ideas together. And you begin to be able to see how to do richer problems with just composing the symbols together. And if you go to something like applecart.info, you can literally type in a keyword, and it will show you various idioms related to that keyword. And once you begin to have these idioms in your head, we can start to do the type of equational reasoning that Iverson was talking about, right? And what that means is you begin not only to learn that this idiom does this thing, you begin to learn that, this idiom describes this property about this other thing that was another idiom. And this idiom is equivalent to this idiom. And so you begin to make a bunch of formulas that are equating one concept in APL to another concept in APL. And you begin to get this body of equalities or relationships and build a graph in your head of how all of these things relate to each other. So to take a simple equation, replicate, so on the left-hand side, if we have a set of elements v, vector v, and we want to replicate each of those elements according to a certain amount by the corresponding element in x. So if we had like 1, 2, 3 as x, and the element 5 or something, we would replicate 5 or 5, 6, 7 or something. So we replicate 5 once, replicate 6 twice, replicate 7 3 times. And we would end up a 5, 6, 6, 7, 7, 7, or something like this. Now this happens to be exactly equivalent to this expression on the right, which is expressed using the flattening operation and a reshape, right, and map. So it's just a more verbose way of saying this replicate. And it's using nested arrays instead of the flat representation. So we're sort of connecting various different primitives to see how they relate to each other to compute the same results. And an example of where this might come in handy is suppose that you need to get this j is an index vector. It's a set of indices, and we need that j, but we need to compute it derived from this replicate concept. So we need to find a j such that this equation holds, which basically means we're trying to find the starting point of where all these replications begin in the result vector, which sounds kind of funny, but like that's the kind of thinking that you would think of in APL, of a problem that would arise while you're trying to solve these things in a loopless fashion, right? So this problem might naturally arise in the course of trying to solve a problem. And it's this kind of problem that you need to be prepared to solve as you're doing your APL if you want to stay loopless. Because otherwise, you just have to revert to loops and do each thing incrementally. You have to think about the mathematical equation to lift yourself out of that. And it turns out, if you just look at the exclusive scan, that's exactly the j that we want, which means that the scan operation is connected intimately to the replicate operation using this interesting pattern, which gives us another way of thinking about our code. So once you have all of this, the problem is, how do you use those idioms at scale? Well, if you do a whole bunch of data abstraction, all of these idioms become useless anymore because these are all defined over the array type. And if you suddenly build up an abstraction with a bunch of type operations or functions over specific types, those idioms no longer apply because you've hidden all of that. So to actually use all of this stuff, what you need to do is need to go in reverse, and you need to find a way to take your domain and encode it into the array domain such that you maximize the degree to which the idioms and the primitives have a meaningful interpretation in the expected domain, right? In the encoded domain that you're working with. So you're trying to find an encoding that maximally allows you to leverage the APL primitives and think in that domain. And the one that I spend a lot of time in, and I'm kind of known for, is the tree domain, right? So the tree domain, let's say that we choose an encoding like this, where we think of a tree as just a parent vector, where each element in that parent vector is an index into that vector that points to the parent element in the tree. All right, so if we have like one root node and two child nodes, and the root node is the first node, it's going to refer to itself, so it'll be 0. And then the second node will be 0 because it's also referring to that parent. And then the third node will also be 0 because it's also referring to the first parent, right? But if we chain them together, it might be 0, 0, 1 because it might refer, the last node would refer to the second element and so forth. And that's good to hold the structure of the tree itself, but not the data. So let's say we just introduce a little bit of data and say we have a type vector that says what type of node we have at each given place. Right? So this is saying that our nodes might be atoms, functions, expressions, or primitives, say. Something like this. And so then we can write something like this. And to a non-APLer, it's actually not too bad, right? You've got some t that you're testing equal to e and this. It reads like a Boolean logic expression, except for that little squiggly at the beginning. But we know that that little squiggly is the where operation, so it's just going to return the indices of all the non-zero elements of that Boolean mask. But we're encoding, so we're not going to think like that, right? That's not how we're going to think about this. When we read this, and we're in this tree domain, right, this expression takes on a whole different interpretation, right? So now we read this as the nodes where the type is an expression and the type of its parent is a function. Right? So we remap these concepts into the domain that we're working with, but we don't actually change the symbols. And that's really key to maximizing your leverage of APL. And this is how I get loopless stuff. Because now, you'll notice, let's not do that example first. You'll notice that we are basically leveraging all of the basic APL semantics to model tree operations that we care about. In this case, it's just a query, it's a traversal with some information that we want. It's a selection over the tree, right? Or a tagging of the tree, if you will. But when I see that, I don't have to map between the domains. I've already mapped this iota underbar symbol to mean I want to get the nodes that meet this criteria. I don't see, oh, the where function that's going to take a Boolean. I don't read it like that, right? And these, when I say t equals e, I'm not thinking, oh, this other thing. I'm thinking, I want my type to be an expression, right, for any of the elements I'm looking at. And when I say t sub p, I'm not thinking some array vector operation. I'm thinking the type of my parent, right, as a node. And if we scale this up even further, this guy, here's our parent vector, and say this is I, which is a subtree, or a subselection of elements that represents a subtree inside of my AST, or inside of some tree in general. Turns out, this searching function, the index of, which is going to look for these look for things here that appear in here and give us that index back. Well, all that's doing is it's literally just recomputing a fresh, independent tree from that subtree, right? And if anyone wants to see a worked example and we have time at the end, I can be happy to show the intuition for that. But what that means is we're mapping a relatively complex idea, which involves like pointer rewriting, edge rewriting, and all things, into a single APL primitive. And we do this without introducing any of this new syntax and no new abstractions, boundaries on top of all this stuff. And of course, we have to do this also for control flow. And so it's the same basic idea. We use things like booleans, indices, and shapes to handle concepts that you would normally introduce more abstraction to handle. And that allows us to leverage all of our implicit loopless stuff for these various problems, like conditions and branching and managing pointers and partitioning and grouping and slicing and all that. And so if we think about that in terms of here, we've actually encapsulated things like tree traversal and iteration and types and pointer chasing and relationships and object IDs, all by encoding them into the domain of arrays without an extra layer so that we can then use all of our array primitives to do that work. And where can this go wrong is if you design your large systems incorrectly, you might be able to do this in the small, but then all of a sudden you can't chain these together and things get complex. So architecture can really mess up your simplicity here because you make your architecture too complex and then it ends up getting horrid anyways. So this is really about dependency management. And in the same way that we have a very nice linear or mostly linear data flow description of our computation at the line level, the idea is to scale that pattern as far up the architectural hierarchy as you can. So to continue to scale this, you continue to push that model of data flow as high up in the architecture as you can get away with, right? Which essentially amounts to minimizing your dependencies in your graph at any given level of the architecture that you're designing. So you aim for linear, but if you can't get linear, you try to get a tree. And if you can't get a tree, minimize the number of cycles. And if you can't do that, well, something is crazy somewhere, right? And in a compiler, fortunately, making the linear flow is actually pretty straightforward. You go through a tokenizer, a parser, do the compiler, do the code generation, do the backend, assembly, if you will, link it all together, and you're good to go. But in APL, we take it a step further and say, okay, no, but even for all of these other pieces, it's all going to be linear, right? So the tokenizer, just pass after pass after pass, linear data flow. The parser, pass after pass after pass, linear data flow, and so forth, right? So that the whole thing is just one giant linear flow. Now, you can't do this in every context, keep it strictly linear, but in a lot of contexts, you can get it almost exactly like this with some very limited exceptions.
It sounds like you're arguing that the native Nano-pass architecture in particular is in APL.
That the Nano-pass architecture is APL?
The place where the Nano-pass architecture feels most at home is in APL.
Yes. You have to do a lot less work to leverage Nano-pass ideas in APL than you have in any other language. And we'll get to why at the end if I make it. So if we're going to do a fully worked example, which unfortunately is not fully worked, here's an example of a problem that everybody thinks of recursively, right? Is function specialization. You have to create a whole bunch of different specialized versions of a given function. And in our case, we're doing this recursively. We're going to do a naive version of this. So we're not going to worry about trimming the tree. We're just worried about producing all the specialized versions that we can recursively in a nested set of functions. So in our case, we have these types of functions that we're dealing with. And we have to replicate or specialize that number of versions for that function, right? So some functions need 2 specializations, some need 4, some need 8, right? And from a programmer standpoint, you don't have to understand why, but you just have to remember those numbers. So now if we were going to implement this in our traditional forms, well, we would just have a recursion that would traverse down the tree and then populate out a new tree that gave us the replicated forms. If we were doing this in, like, say, a traditional functional style compiler. But we're not going to do that because we don't have that. We're loopless here, right? So the first thing is we're going to model that control flow in a vector. And so we're going to get our replication counts. So all nodes have a replication count defaulting to 1 at the beginning. That's how you can read that. Then we're going to look for our function nodes. And based on the kind of function that we have, we're going to give it a particular replication count. So now all we have is every node in the tree, we know exactly how many times we want to replicate that thing. But this is recursive, right? So just replicating yourself that number of times doesn't work because you might have a parent that's also replicated like more times. So if your parent was replicated 4 times and you need to be replicated 4 times, well, then you actually need to be replicated 16 times, right? So what this does is we start with our individual node replications, and then we do a tree walk up the tree, and we specifically don't walk the whole tree because R is like a parent vector, but it's a skip up the tree specifically to just the function points, right? And that is one of the benefits of a method like this, is we can have lots of different ways of walking over our thing and reify those different walking patterns. In this case, so all we do is we visit all of our parent functions, and we include that replication count by multiplying it with ourselves. So then we just go up and it's like a scan over our subtree path. It's formally a multiply scan over our subtree path along the functions, right? And we do that for every single node. So now, what we did there is we essentially now have encoded the recursive pattern that we will see, the recursive call graph, in X as a replication vector. But we know we're going to have to actually talk about the groups of these things and where each one points to. So we use that idiom for the exclusive scan to find J based off of our replication counts. And that'll give us the starting point of all of our replicated nodes. But we also need to know which node we are inside of that replicated group. So that's RO, or offset. And then we do the replication. And this is the actual AST field structure that I would use in the compiler, which is the parent, the type, the kind, the data. This is the symbol table. The R is our reference, the lexical scope, the variable bindings, our replication count, and then the position and end in the source code, where this node originally derived from in the parser. And what I do is I simply say, for each of those elements, I want you to use this to replicate all those elements out and store it back into that variable. So now we just took our tree and we went and exploded it out. So then we blew our parent tree. Our parent tree is now invalid. We've destroyed all the edges. So this pass just computes where your parent should be and puts it back in. It updates the edges. And for slightly more complex parents, we use this exact same pattern, but we have to compute it slightly differently because we're using a different route if we're variable references, which is another set of pointers that we have lying around. And then finally, all we have to do at the end is say, OK, now for all these newly replicated functions, let's say, sure, we tag them with the appropriate type that they now have. And so we've now done what amounted to a recursive algorithm, but fully loopless and data parallel in basically a linear style with one fixed point operation. And so then in the compiler, this little piece of code is sitting there in the parser. So what's our little secret sauce here? Why are we able to do this at scale? Why does this work as a whole? And unfortunately, one of the reasons this works is because it actually fits into a visual representation that I can think about and I can see up and down. I can read it, and I don't have to read a large chunk of this. Because being able to see the patterns and relate all of these pieces together is critical to being able to do more complex operations here. If all I had to do was a small thing, the more verbose code would be fine. But the moment I want to do 20 or 30 of those passes all together to compute over a much more complex idea, now I want to be able to see how all the data flows there and predict that behavior without a lot of things in the way. And so, unfortunately, that whole concept, unified economic simplicity and tersity, right? That is the first thing everybody gets rid of when they decide they want to improve APL or borrow it. Is they try to get rid of that. But that's the only thing that makes these ideas scalable in the large, my claim. Right? If you're not going to use this in the large, you can get away with that. So NumPy kind of does that, right? NumPy is like baby ad hoc APL in the small for very specific domains, right? But it's very hard to use NumPy effectively at scale as your primary general purpose programming language. Whereas in APL, the reason we can do that is largely because we're representing this differently at the notational level. We interact with it differently. And a lot of this comes straight down to when the code gets small enough and simple enough, it's a lot easier to deal with. And this goes straight back to Iverson's Principles of Good Notation in his Turing Award lecture, Notation as a Tool of Thought. He listed five principles of good notation from a mathematical standpoint. So if a good math notation, say, or a good tool of thought notation. And economy is one of them. People think that means smallest possible size. It only means the smallest effective net size overall, holistic size, not necessarily minimal programming languages, but languages that need the least amount of things to do the most amount of things in practice. And ease of expressing constructs is about directness in your coding, right? Suggestivity is about making those connections between various idioms, right? Ability to subordinate detail is the ability to solve a problem, see the full transaction, see it fully transparently, and not have to worry about those details, even though they're visible to you in some way. You know about those details. You don't have to worry about them. They're subordinated. They're not abstracted away. They're not hidden. They're just not in your way. And amenability to formal proofs is sort of a more advanced concept of your ability to do that equational reasoning that we were talking about. So thank you, and hopefully we can take some questions.
Thank you for the talk. It's very interesting seeing the reuse of symbols in different contexts and your kind of ad hoc redefinition of a subset of the language in a different domain.
Yeah.
That makes sense. Tracks. Awesome. Question is, if you think of the operators and the operations that you can do with those operators, how many holes in that matrix should I expect, or is every operator applicable in every context?
I did some testing on my tree compiler to do I can't pull it up right now, but if you talk to me afterward, I did a histogram of the symbol usage in the compiler in my 17-line version earlier. And I used a large set of the APL primitives. The circular function for trigonometric stuff was missing. So I didn't do trigonometry in the compiler. But the general answer is that as you get to large-scale programs working over these large domains, almost all of the APL primitives are relevant, almost everywhere. If I understand your meaning, you will be able to use almost all of them everywhere at some point. Some of them are very small. So like in the machine learning stuff, it was the first time that I had able to use a 5-dimensional dyadic transpose in a system, which is manipulating the indices in 5 dimensions over a given piece of data. And that was the first time I had used a dyadic transpose at that scale for that thing. But regular transposes appear everywhere, right? So some are much more used than others. Some, you use them internally, but they don't end up in the code. And others, are everywhere. They're really, really pervasive. So if I understand you right, when you do these encodings, I have found that these primitives are so economical that they tend to apply almost everywhere, and you tend to want to be able to use them everywhere. So a problem that we have is people will say, oh, well, I want to write a little DSL to solve this particular problem in my thing, and they come up with a reduced instruction set for that domain, and inevitably, it misses some special corner that would have been solved if you just had not put the DSL and just written the actual APL, because then there would have been another symbol available to solve that problem for you. I don't know if does that answer the question?
Yeah, that highlights, first of all, thank you for the answer. It also, the way of framing this for me as a non-APL programmer is I've learned a foreign language, and trying to fit my language into their language doesn't work.
Right.
You really have to just learn it.
Yeah.
And this tracks. So
Okay.
yeah, thank you.
Yeah, thanks. Did you? Yeah, okay.
So I have a super low-level implementation question, which is, when you have these nested arrays, are you, it's very obvious to me how you can represent a regular rectilinear array, but when you have these nested arrays, are you just storing pointers at each element to the nested arrays, or what is the representation that's usually used there?
So the typical representation is to store a pointer to a ref counted cell, and so you will reuse subarrays in nested arrays that are the same. But there are other representational models, and the general attitude of that, the question, do I need to repeat the question? I don't know. Okay, we've got the mic, okay. So the general principle is nested arrays are usually used at the top level of a computation, not the lower level. So you try to avoid having lots and lots of computation over nested arrays that are highly iterative. Usually you'll do something more like a struct of arrays, and the struct is a nested thing, which is actually, that's what's implied by my, this whole thing is just a particular syntactic reification of a struct of arrays. Yeah. No.
So I've never actually used APL, and my knowledge is what everybody gets, like arrays and rank polymorphism. So that's very interesting to see this like HCI, and as you're saying, you're imagining everything in the array. And I imagine if you're working on it a lot and you know these primitives, it probably makes sense. But can you tell me about debugging? Like, I imagine still, even if you're an experienced programmer, there must be something you're getting wrong. How do you go about just debugging what's wrong? Are you relying on idioms and trying to pick them out? And how do errors look like? Is it your rank doesn't match somewhere? Stuff like that. So
Yes, so that was yesterday's talk actually, in short, but let me just pull that up. Yes, we have this. So this is the IDE, the environment, and this is my parser, which is written in this Nano-pass style. So I'm going to put a stop at the beginning of the parser, and then I'm going to run the parser over some code, and I can walk through the execution of this, like so. And I can also, at any point in here, I can say, print out the tree that I'm parsing currently. And so then I can interact with it like this, and I have access to all of those variables that I was working with and manipulate them. And in future versions of the interpreter, we have a token-by-token debugging, which will allow you to trace through every single execution of every symbol and have watches and see what the arrays are and so forth through the execution. And so this is actually, I would argue this is way easier to debug than your typical recursive functional programming, because there's no call stack that gets in the way, and you just line by line can equationally look at each piece state by state down the line. Does that?
It goes so. And there is a type checker, right, with checks ranks, and if you're getting something
At runtime, yeah. So if I tried to do something like 3, 4, like something like this, it would give me a length error saying that the types are mismatched here. Yeah.
Okay, thanks.
Yeah.
I think that's it.
Okay, great. Thank you.